So the question is, how do you know what to take the derivative with respect to? Okay, that's an excellent question. So with implicit differentiation, the idea behind it is that you've got some equation relating two or more quantities, okay? And you're trying to find the rate of change of that scenario, essentially, of that equation with respect to some given quantity, okay? So we have to tell you what to take the derivative with respect to, unless it's implied, okay? So what would be an implied scenario? Something that would be implied is if I ask you to find the slope of a tangent line, for instance, right? So if this is the question, when we're talking about slope of a line, right, then we're thinking traditionally about graphing on the xy plane, right? So if you have x here and y here, and you want to talk about the slope of a line here, well, the slope has to be changes in y over changes in x, right? So that automatically tells you that if you're looking for a slope of a tangent line, you're going to be looking for the rate of change of y with respect to x because of this background information, okay? Now, what we're doing lately with these related rates problems is we're saying, hey, I've got a whole bunch of quantities that are related to each other, and they're all changing over time, right? And so if I want to talk about the speed at which something is changing, how fast or slow, those words, fast, slow, right? Those are context clues to tell you that you should be taking the rate of change with respect to time. Yes? Right. So let's pretend, for instance, that we're talking about, let's see, like, so here we are in Phoenix, right? And LA is somewhere over here, right? And we want to drive from Phoenix to LA. So I could have some position function in terms of time, right? So I don't know, something like that, okay? It's a very basic function. But this is a function that gives my position from Phoenix to LA as a function explicitly in terms of time. So when I look at this function, it would be really easy for me to talk about the rate of change or the speed because I'm already throwing time at you, right? But in other situations, or even in this situation, it might not be as explicit. I'm making it explicit because I want an example. But let's say that, for instance, I wanted to think about not my position between Phoenix and LA, but rather the distance, if you will, between, where's Tucson? Tucson's down here. Tucson, right? So let's say while I'm traveling, I want to pay attention to how fast my distance is changing between LA and Tucson. Let's say I have a friend in Tucson and I care about how fast I'm running away from them, okay? Well, then now I've got a whole bunch of quantities at play, right? I've got the distance between Phoenix and LA. I've got the distance between Tucson and LA. And I've got the distance between Phoenix and Tucson, which is always constant. Thank goodness, right? Lest there be a really big earthquake soon. Okay, so then in this situation, right, I've got two quantities, this first distance and the second distance that are changing, right, as I make my journey from Phoenix to LA. And I may or may not have an explicit, let's say I don't know explicitly how the distance is changing from LA to Tucson. Okay, but I could like model this situation, and let's pretend for a second that this is really easy and this is like a right triangle. Okay, that's 100 miles. So then I have a relationship between these distances, right? I've got this type of relationship, okay, where I know something about the rate of change of the first distance. And then if I want to find the rate of change of the second distance, I can now do that. So when we're doing these related rates problems, you may or may not have an explicit formula about how things are changing with respect to time, but you can certainly imagine that they are changing with respect to time. I don't know if my little rant just helped or not. Is this helping? So just notationally, when we use this d over d notation, right? So the thing that goes on top is the thing you're taking the derivative of. So derivative of this thing. And then the thing that goes down here is the with respect to. Okay? So when we say like, dA, dr, and we're talking about the area of a circle, right? So this would be the rate of change of the area with respect to the radius. So that would tell me how fast the area is changing with respect to the radius. So if I got some numerical value, then that numerical value would tell me for little changes in r, the area is going to change that numerical value times as much. Right? Yes?
Let's say that we will be like count our little differences. Is there a way to test if it's right? With the information we have at the time, is there a way to test it?
Like, okay, so are you talking about the related rates problems, or are you talking about implicit, like finding the slope of a tangent line problem? Well, you could give yourself a visual, like, this looks like it should be right, by, if you find the slope of the tangent line, right, then you could actually write down the equation of the tangent line and graph it up to the curve in graphing calculator. So let's say I have, just because these are the easiest ones to graph, guys, sorry. It's not an interesting new example, right? So let's say I have this curve, and I want to know, what do I want to know? I want to know the slope, or I want to find the equation of the tangent line when x is 2 and y is negative. Okay? Why did I have to put that second restriction? There's two options, right? So if I'm talking about the equation of the tangent line when x is 2, that doesn't make any sense, right? Because there's two places on the curve where x is 2. So there's two tangent lines that I could be talking about. So by doing y is negative, I'm talking about the one in the fourth quadrant, okay? So then what happens? So if I want to find the equation of the tangent line, we just talked about how, that's looking at changes in y over changes in x. So in order to find the slope, I should be looking for dy dx, okay? So if I differentiate this equation with respect to x, the rate of change of x squared with respect to x is 2x. The rate of change of y squared with respect to x is 2y dy dx, right? And so again, a way that you could think about that is it's the rate of change of stuff to the second power, right, is 2 times the stuff to the first times the derivative of the stuff. This is the chain rule, okay? and the rate of change of a constant is 0. Okay, so if we solve for dy dx, we get what? Negative x over y. So I have an x value to plug in, but I still need a y value. How do I get the y value? Plug my x into where? The original equation, right? I want to know the y coordinate of this ordered pair, right? So that ordered pair is 2 comma what? I'll do the easy part, negative. But we really don't do mental math, do we? No? Yeah. It is really loud, and I have no idea where it's coming from. No? That didn't help. I don't know. I'm sorry. It is obnoxious, though. I agree. Ooh. I've got everything on mute, and changing the lights didn't help. Any other ideas? Hmm? Yeah, I don't know. Should I talk louder? Will that help? Bah. Okay. Mental math? No mental math. What's y? Negative? I am a little concerned. Yeah? How we doing? Okay, so there's a point, right? X comma y values, so we can find the rate of change at that point is going to be what? So I'm going to write it this way. Negative 2 over negative root 5, right? So that gives us a positive value, which should align with our thinking. Because if you were just like visually estimating, right, then you would sketch in some sort of, tangent line, like so. It certainly has a positive slope, so that's a good start, right? Okay. Now, if I actually wanted to check for reals, then what would I do? I would, whoops. I would type in the equation of the tangent line and graph it, right? So let's do that. So what's the equation of the line? I'm going to start calling on people again. Harrison, are you here? Equation of the line? For this, I want the equation of the tangent line at the point 2 negative root 5 for the curve that we're talking about. Okay. Philip? Equation of the line. Mm-hmm. It wouldn't let me, sorry, x minus 2. Voila. Right? And so now if I want, I can zoom in on it. And check it out. The more we zoom in, oh, I wasn't at that point though. Let's get back. This way. So right here is x equals 2, abouts. And when we zoom in, you notice that that line and the curve practically the same, okay? So that's this idea of local linearity, that when you zoom in on a curve, anywhere on the curve, whether or not it's a function, if you zoom in close enough, that curve is going to start to look a lot like a line, right? And so we can approximate it using tangent lines, okay? And of course, we use the rate of change of the function at that point so that we actually get a good approximation, right? Because the curve itself is behaving one way. So if we write the equation of a line that behaves in a similar way nearby, then we're going to get a good approximation. Okay, so hopefully that was helpful. And hopefully that helps you see a way that you can use graphing calculator to help you check your work. Okay. All right, so then what I wanted to do, because I was looking at your My Math Lab homework scores for the homework due today, and it wasn't so pretty. So I was thinking that we could continue practicing some related rates stuff before moving on Friday to some more fun and exciting new things. But let's practice a little bit more first with related rates so that we can make sure we have this down solid, okay? So on Monday, we started with this handout. Hopefully you still have it, because I don't have any more copies. Marissa, did you give them all away, or do you still have any? Okay. Does anybody need a copy? Marissa has some, but only enough if you weren't actually here on Monday. I didn't make enough copies for people to have two. I like trees. I try to save them when possible. Okay, so on Monday we talked about the first problem where we were going fishing, right? And we threw a pond and a lake, and we talked about that one. Okay, and so then we actually started fishing, and we caught a bike tire. That was pretty lame. And I believe we got as far as finding, did we actually find how fast the tire was moving when it was 2 feet from the dock? We did not? No? We got to the end of the second page. So we found out that the relationship between, so if I was looking at a picture of what's happening, here's my fishing wire, right? We called that Y. We called the distance from the tire to the dock X, and the dock was 3 feet high, right? And so we had this relationship that x squared plus 3 squared is y squared. So then if we differentiate both sides implicitly with respect to time, what equation do we get? Use 2y dy dt equals 2x dx dt, right? And so, so we have a related rates equation. This is a related rates equation. Why is it called related rates equation? Because there's rates, and they're related. Super cool, okay? So then what? Now that we have an equation relating the rates, now we can actually start doing some work, okay? So Oh, that worked nicely. Okay, so how fast is the tire moving towards the base of the dock when it's 2 feet from the dock? So what are they asking for? Yeah, so saying how fast is the tire moving towards the base of the dock? Well, the distance of the tire from the dock is x. So how fast it's moving is going to be the rate of change of x, right? So this is asking for dx dt. Is it asking for the formula for dx dt? Just a value, right? So that means it's asking for dx dt when something is happening. When what's going on? When x is 2. Okay? So that gives me some guidance as to what I still need, right? Because I have this related rates equation, but, and so they've given me a value for x. I want dx dt, but hey, when I look at this right-hand side, I still need a y value and a dy dt value, right? How can I find y? Go back to the original equation, right? So what does y equal this time? So in general, it's the square root of x squared plus 9. But I care about y when x is 2. Right? So now I have a y value. I still need the dy dt value. Right? Question? So x is 2 squared plus 3 squared is y squared. So 4 plus 9, 13. And I know to take the positive square root because y is representing a length. Right? Y is the length of the fishing wire. So it must be positive. Dy dt? How fast is the wire being reeled in, right? That's what dy dt represents. Do we know that? Yes, we do. It was given, right? We were given that dy dt equals what? -2. That was part of the setup of the problem, okay? So we want dx dt when x is 2. We're given that dy dt is -2. We were able to solve for y by using the original equation. So now we have everything we need to be able to actually find dx dt when x is 2. We can answer the question now, right? So dx dt, I guess I might as well just plug everything in. So when x is 2 is 2 times root 13 times -2. And so then we can solve for dx dt. So we get what? Negative rad 13. Okay? Does it make sense that it's negative? How do we interpret the fact that we got a negative number for dx dt? Mm-hmm.
Based on the way we set up our equation, away from the drop off is the positive direction.
Okay, so that's a good contextual interpretation. Yeah, let me give you the mathematical version, which is that x gets smaller, right? So I'm not saying that what you told me is wrong, right? I love it, and that's exactly how I used to do it. But what I've noticed is that sometimes that confuses people in other problems when they don't just think about when they think about the context instead of the quantities. So I'd like you to be able to do both. Okay, so think about the context. So the context is the tire is moving towards the dock. Okay, that means, however, that x itself is getting smaller. It's decreasing. Okay, so that's that negative. Beautiful. Question? Oh, you're talking about having a distance and a rate in the same equation? Right. Yeah. I did not use this equation to find y. I used the original equation relating the distances to find y, right? So what you're sort of combating with is the reality of the situation, which is the fact that the rates of change with respect to time are not solely dependent on time, right? Because, well, in a way they are, because everything in this situation depends on time, right? So technically, x is a function of time, and y is a function of time. So when we're talking about rates here, we're talking about rates dependent upon time, implicitly. Okay, now the handout keeps going in that it asks you to sort of repeat this process for different values of x, right? So is the tire moving faster as it gets closer to the dock? How would you answer that question? Or how could you try to answer the question? What would be a strategy? Beautiful, right? So the scientific method, okay? So we already found the rate of change when x was 2. So if we find the rate of change when x is 1 and compare the values, we can see if the rate of change got faster or slower, right? Or stayed the same. And so that's how we can answer that question. Question D can hurt your brain. So I'd kind of like to skip it. But here's what I'll say about it, right? So we found that dx dt was, what was it, negative y over x, dy dt? So at the instant that the tire leaves the water, x has a value of 0, right? And y has a value of 3. That's an undefined numerical value. So what you have to do in order to answer this question is continue the process that you started in C and keep testing values as x gets closer and closer to 0 to see what's going on, okay? And that's how I would suggest you approach that. Okay, what about how fast is the tire moving after it leaves the water? Is that question still asking for dx dt? No, right? What's it asking for? dy dt, which is negative 2. Okay, so that one's nice and easy. Okay, you just have to pay attention to what's actually going on, right? Okay, so much for fishing, right? So you decide to go to a ball game. You buy a snow cone. Is this helping me doing these problems up here? Would you rather be doing them together and then? Okay, here's the trade-off. If I keep doing problems up here, then the note on the homework saying that you only need to do 5 of the 8, that goes away. You do all 8. So now you want to work together? Okay, well, we only have 15 minutes, so if we're going to do that, we're going to do it really fast. Are you guys super awake and we can like bust through these as quickly as humanly possible?
So the homework that we'll have this Friday, are they on the same level of difficulty as these ones? Because I felt like the homework that was due today was infinitely harder than
They're the same problems.
They were. Then let's run the bases, shall we?
Okay, let's run the bases. Mm-hmm. Mm-hmm. Yeah. Are we doing the homework problem? Is that what you're telling me?
Well, I'm just, because you just mentioned it, it's like super hard to answer the question.
I don't know how to make this bigger. So you're talking about part C?
Part C, finding theta number B, theta 2.
Okay. So we've got a right triangle. Here's theta 2. Here's theta 1. X. This is 90. So tan of theta 2 equals, it's x over 90. Oh, okay. It doesn't matter, right? Does it matter?
Well, if it's x 90 over x,
Then it's undefined when x is 0. I agree.
so how do you solve for it? Or do you just have to use a different string of
Yeah, use something else. Okay. Does everybody know the problem that we're talking about right now? You've all hopefully looked at it. You didn't look at it? It was due this morning. So the rate of change of the left-hand side with respect to time is what? So far, so good? Okay. What's the rate of change of the right-hand side? Okay. So, right, because you need to have a theta value to plug in for secant squared, right? So, okay, so we're trying to find this value, right? This is the value we're trying to solve for. They give us dx dt in the setup of the problem, right? So we just need to know this value. Now, when we need to know this value, though, when the player slides into base, into second base, right? So x is 0. What's secant? 1 over cosine. Cosine is cosine. Wait, what?
The inverse tan of 0 divided by 90 is 0.
Oh, you're coming back up to here?
Right.
Okay. Secant squared of 0 is 1. Right? Secant of theta is 1 over cosine of theta. Cosine of 0 is 1. So secant of 0 is 1. Secant squared of 0 is 1. So this whole thing is 1. So then we're done. Okay. I haven't figured out how to turn that off and on. I didn't realize it wasn't on. I'll look into it. Yeah.
If you go to the chapter work and under 3.10, it's there. Just show me how to do it. It's there.
Oh,
So it's in the work. It's in the chapter.
tell that to your classmates one more time.
Okay. Are you able to go to it? If you
I think my stuff looks different than your guys' stuff.
can go to the chapter review link and hit on it and go down to whatever chapter we're in, like chapter 3. This is 3.10. So all his questions are in 3.10. You still have to go through and solve and play around with them, but that little icon there showing how to do it pops up.
Like actually in the text.
Yeah, it's like 13 steps sometimes.
Beautiful. There you go.
Where is it?
In the online.
I have it up right now.
Which problem do you guys want to do now? Yes. 5? Looking at the blimp. Draw a picture. What does it look like? Just gonna So there's a start to a picture. What else should I be labeling? The angle of elevation for my line of eyesight, right? So that's this angle right here. So I'll call it theta. Anything else I can label? X value. So X value representing the distance between myself, the horizontal distance between myself and the blimp, right? Not the actual distance, because that would be this slanted distance, right? So the horizontal distance between myself and the blimp, okay? All right. So what we were given, I've already labeled some of it, right? The elevation of the blimp is 1,000 feet. And that stays constant, so that's why I could label it as a constant in the picture. Did they give me anything else? So 880 feet per second is dx dt. Is everybody okay with that? Is it positive or negative? Positive? Jonathan, what do you think? Positive or negative? I asked what Jonathan thought. Jonathan? No? Okay, what did you say? Positive because X is getting bigger, right? The blimp is moving away from you, so X is increasing. Okay? I like it. All right, what do we want? Rate of change of angle of elevation. So how do I write that mathematically? d theta dt? Do I just want a general formula for that for whenever? When theta is pi over 6. We always work in radians with trig functions, okay? So we'll use pi over 6 radians. So, all right, so that's our setup. That's what we want and what we know. What we were given and what we want. So now we have to bring our own knowledge to the table. What do we know that can relate the corresponding quantities? So what are the quantities in this situation? X and theta, right? X and theta are the associated quantities to these two rates of change, right? dx dt and d theta dt. So x and theta are the quantities. What do I know that can relate to those quantities? Tangent of theta equals 1,000 over x? Yeah, you could do it that way. Oh, yes. You have lots of choices, right? You could have used, what else? Cotangent of theta, right? That would be x over 1,000, and then you don't have to worry about x being in a denominator. That's another choice. Just saying. Okay, so, but that's what I know, right? So then how am I going to get from what I know to what I want? Taylor J., are you here? No? Lauren? Kaiser? How do I get from what I know to what I want? Take the derivative of both sides with respect to time. Finally, calculus, right? We haven't done any calculus yet, so we got to do calculus now. So which one did you want to use, the tangent or the cotangent? Cotangent? Okay, so what is the rate of change of cotangent of theta with respect to time? Actually, I'm going to just do it down here. What is it? Negative cosecant squared theta d theta dt. What do you get on the right-hand side? X over 1,000? One 1,000th dx dt. So in order to find d theta dt, what can we do? Are there questions? How are we doing? You okay? Good. We have dx dt, right? Remember that was given. So I can plug in that. I can plug in this. Oh, and then I can solve. Voila. Okay. So that means that d theta dt is what? 1 over 1,000. Dx dt was 880. And then I'm going to divide all of that by negative cosecant squared of pi over 6. And I'm going to type that into a calculator if I feel like it. Make sure my calculator is in radian mode, and then get a decimal approximation. Okay? But that's it. See, these aren't so bad. What's the hard part? The hard part is identifying what did they tell you, drawing an appropriate picture, figuring out exactly what they want, and then coming up with the equation to relate the quantities. Once you've done that, though, It's literally you take a derivative and you plug stuff in. That's it, right? So that's why the mastery test is so important. So for those of you who are still taking it tomorrow, make sure you study hard, pass it. And if you still want to talk to me about what mistakes you made on the first go about, you should do that, right? Because we've been catching everybody who's come in so far. It's just been like silly mistakes. Oh, you memorized the derivative of arctan wrong. Whoops, that's a problem. Or mix up the negatives. Or sometimes it's something a little bit more serious about the chain rule. But if you come in, I promise we can talk about it, we can sort it out, and we'll get you right back on track, okay? Wait, what? Oh, just because I didn't want to have to deal with taking the derivative of 1 over x.